Okay, in this lecture, I will continue from what we have left last time and talk about virtual memory concepts. In the previous lectures, we have been discussing on paging in random access memory and the relation between logical memory and physical memory and the concept of the memory management unit. In this week, we will be talking on virtual memory concepts and its applications. In the Silberschatz book, we have concepts on why we are using virtual memory. That part we already covered in the last part of the previous lecture. We will be discussing on copy on write, page replacement, and allocation of frames, trashing, and other considerations. The reason that we use virtual memory is the size of the physical memory is smaller than we want. So we will talk about that. The solution will be page replacement algorithms. There are page replacement algorithms that may come in questions in exams in many places. So that is interesting. Also, the concept of working set model is interesting. It is introduced by Peter Dunning. And he is still a good advocate and writer on working set model. And the working set model can be applied to many other places in computer engineering domain and other engineering and science domains. And we will be discussing on examples on shared memory and memory mapped files at the end, and how kernel memory is managed will also be studied in this chapter. Normally, what was the difference between a process and a program? Can any of you tell? Probably not. Process means program in execution. So if the program is in running state, we call it as process. And in order for a computer to execute a process for a particular time, it has to be in the random access memory. So accessible memory, it could be in read-only memory as well. So it could be in memory. It should be in memory. A program must be in memory. The code needs to be in memory to execute. However, entire program rarely used at the same time. Therefore, part of the code that is necessary for a particular amount of time, which we will say working set model later, should be in the memory. Therefore, we say entire program is not required to be in the memory. Therefore, when we have 2 gigabytes, 4 gigabytes, 1 gigabyte, and 3 gigabyte applications, these are applications as theoretical sizes. So 2 plus 4, 6, 7, plus 3, 10. 10 gigabyte of applications. Can they run on 8 gigabytes of RAM at the same time? The answer is without virtual memory, no. But with the virtual memory, the answer will be yes, because these applications are so big applications and not all the parts are necessary to be in the memory all at once. Parts of the application can be loaded. But the question is, which part? So that brings the algorithm of paging structures and page replacement algorithms on this topic. These are the principles. I'm going to go over that. Only part of the program needs to be in the memory for execution. Logical address space will be much bigger than physical address space. For example, in logical address space, you have in 64-bit architecture, you have 2 to the 64 bytes of memory addresses, addressable logical memory. Although some parts are reserved, not used, but it can happen. Therefore, it's too big. But when you have small amount of memory, like 4 gigabytes, you have 2 to the 32 size of RAM. So what you will do is you will put some of the logical memory pieces as necessary to part of the real memory. The rest will be stored, the copies, the rest will be stored on hard drive. Sometimes this is too big and unnecessary. So what they do is they store 2 to the 48 on disk, maybe 2 to the 34. Store this amount of information on hard drive as the virtual memory and copy, activate 2 to the 32 of it on random access memory, which is fast memory. And whenever you need, make replacement in both directions. Therefore, this technique allows address spaces to be shared by several processes, and logical address space becomes much greater than it is. And when you start processes, the whole code, the whole program is not required to load into memory. So program can start a little bit faster. Many more programs can run on the same memory at the same time, concurrently. Well, not at the same time, but the concurrency. What is the difference between parallel and concurrent? What do you think? Evet arkadaşlar, orada mısınız? Televizyon mu izliyorsunuz? Ne yapıyorsunuz?
Merhaba hocam.
Merhaba.
Yani paralel olan hocam tamamen eş zamanlı olarak çalışması. Yani tamamen eş zamanlı. Concurrency araya yani çok sık değiştirerek paralelmiş gibi hissettirmesi diye anlıyorum.
Evet. Arada yani task switchingle çalışırsa
evet, çok sık değiştirerek
diyebiliriz. Prosesler açısından aynı anda ama aslında değil. Ama paralelde ise gerçekten aynı anda çalışma şeyi var, durumu var. Tabii bu bazen yanlış kullanılabilir, masum bir şekilde. Masum olarak yanlış kullanıldığında da kullananın kafasına vurmamak lazım. Yani orada kontekst tabanlı ne demek istediği açıktır. Ama tabii makale falan yazarken, düzgün bir metin hazırlarken paralelle concurrent lafını dikkatli kullanmak lazım. So, when you only load the parts of the code to memory, when you need, so less I/O needed for loading or swapping processes, because, for example, when you have a 4 gigabytes of program, when you are unloading that program from memory, that 4 gigabyte is not the issue. Only, for example, 500 megabyte of the program is in the memory. So when you are going to swap it out or swap in, only part of the big application is transferred between hard drive and random access memory. We have, this is traditional, physical, we have logical. This transfer is done by MMU. In the virtual memory, this is for paging. These are pages. These are frames. And there is page table. So it shows what is where, and memory management unit checks is in relation with the page table. When we have virtual memory, we also have virtual memory file. So not only physical memory, but also we have the memory on disk drive. On disk drive. So that could be at the same size with the logical memory, or could be smaller than logical memory, but bigger than physical memory. For example, when you have 8 gigabytes of physical memory, you may have 16 gigabytes of virtual memory file, or 64 gigabytes of virtual memory file on your hard drive. So 4 times, 6, 8 times, 16 times, depending on what kind of application, and data is stored and operated on your platform in operating system, what kind of applications are run, it can affect. In reality, you can adjust virtual memory file size to suit your needs in the platform. When you install Linux at the beginning, as I remember, it usually asks a number, and it defaults to a number which is twice as big, or twice or 4 times as big of the real physical memory. So it is not, although it can be, it is not 1000 times of physical memory.
Hocam bir şey sorabilir miyim? Virtual memory alanı tamamen rezerve edilmiş oluyor değil mi? Yani oraya başka bir şekilde veri yazma şansımız olmaması lazım değil mi bu durumda?
Disk sisteminin erişimi disk sistemi interfeysi üzerinden direct memory access controller'la, disk controller'la, dolayısıyla diskin üzerindeki virtual memory file'ı da şeye tabi, diğer file operation'larına tabi. O da bir file yani. Dolayısıyla yazamazsın. Çünkü owner'ı farklı. Ama zannediyorum root şeyiyle çalışan bir program virtual memory file'ını yazabilir. Yani root'la çalışırsa yazabilir diye düşünüyorum ben. Çünkü o da bir file.
Teşekkür ederim.
Daha üst bir koruma varsa onu bilmiyorum.
Genelde hocam bu yani RAM yetersiz geldiği zaman mı virtual memory oluşturuluyor yani disk üzerinde?
Evet, şöyle bak bu şekil güzel. Logical memory'miz daha büyük. Neden daha büyük? 64 bitlik bir mimarimiz var. 2 üzeri 64. 2 üzeri 64 kaç sayı biliyor musunuz siz? Çok büyük bir sayı. Yani çok büyük bir sayı. Ben şu an geçen gün hesaplamaya çalıştım. Beceremedim. Bir yerde de okumuştum ama onu tekrar bulamadım. Yani öyle böyle bir sayı değil. Dolayısıyla o kadar hafızamız, bırakın RAM olmasını, şey bile bulamayız. Disk de bulamayız. Şu an için bugünkü teknolojilerle. So you have logical memory, but the application space only uses part of the logical memory. So it is practical logical memory for the architecture. The rest is reserved, but practically all the programs believe that they can go up to, for example, 2 to the 40. Above 2 to the 40, nobody cares. So your memory management unit is probably limited, not theoretically, but in practice. So your logical memory is like that. And your virtual memory is a little bit smaller than that, so that it will be manageable in size as a file. That virtual memory is bigger than physical memory. That is for sure. This is bigger than physical memory because otherwise it is not necessary. Physical memory'niz 8 GB, virtual memory'niz 64 GB. So that means you can run your applications as if you have 64 GB of memory. What will you do with 64 GB of RAM? What will you do with 64 GB of memory? For example, you are doing machine learning, and the machine learning, you need to load the data set into the memory as an array, big data in memory. But you have 8 GB, so 8 GB is not sufficient. Do you use that 8 GB, that big data, all together? The answer is maybe yes, maybe no. Usually, if you are clever enough, if you are a good programmer, you watch out. So in the memory, you try to use blocks that are near each other in the data set. If you have such a big data in the virtual memory, and if you pick one data from here, another data from here, another data from here. So if you very if you are very if you are very scattered in memory, the efficiency will be low, because in order to access to those parts, the parts will be brought to real memory and used. So swapping in and swapping out will be more required in those cases. And I will come to that part. Did that answer your question? So this is your hard drive. Again, 64 gigabyte virtual memory file. Not the whole hard drive. That is a part of the hard drive. You can reserve an additional hard drive for a complete virtual memory disk, so that it won't be affected from minute to minute disk file operations, and it can be connected to another disk controller so that it will be fast enough and dedicated to virtual memory operations. That is disk supported memory, directly disk supported virtual memory, which can be necessary for certain applications. If the application requires a lot of layout in the real memory, then that is the way to go. So heap, top of the memory, that is the old-fashioned, where the address increases. I like this way. I don't know why. As if we are making a building. That is the first floor. That is the second floor. Third floor, like a building, right? So low address is at the bottom. This is the bottom of the memory. You understand what I mean? So at the low part, there is a code, then you have data, and the rest dynamic data, which is heap, some empty space. Then stack is at the other end of the address space. That's the user space. At the beginning, at the location between stack and heap, the current heap, that address is reserved by the application, for the application, but not used. So I can think that, let me give this memory to application and give the rest of it if it is required. If it is not required, let me not give it. For that purpose, again, there will be paging, and those pages will be transformed to virtual frames through virtual memory. Therefore, the utilization will be higher. If the part of the code here, if the part of the code is not used, then no memory is given in real memory. That part will stay in virtual memory because it is not in action. It is not running. Furthermore, you may share pages. Process 1 and process 2 may share a page that page should not be duplicated in memory. Rather, if it is a read-only part, that page can be shared, just like we share pages in the page table. We can do the same thing in virtual memory. One important mistake, that students do is in exams, in the entry exams, when I ask virtual memory, they give answers about paging. That is less likely. But when I ask about paging, they start explaining virtual memory. Although they are related, they are completely two different things. So virtual memory and paging are different things. Paging is done between logical memory space and real memory space, again using pages. In the virtual memory, you still have pages, but there is a hard drive. And size of the virtual memory is bigger than size of the real memory. And size of the virtual memory may be equal to size of the logical memory, or maybe less than size of the logical memory. In the paging, also, size of the real memory can be smaller than, obviously, can be smaller than size of the logical memory. So two different, that is process 1 and that is process 2. Process 1 and process 2 can share libraries through shared pages. So those pages are only can be copied to random access memory in one place. So to save space in the real memory. So the principle is you have to ask for it as an application. You have to ask for it, then the system will take you in memory. If it is not necessary, if you don't ask for it, if you don't ask to bring yourself into memory, that page is not brought to real memory. It will stay in the hard drive on the application. So let's see that this is 4, 5, 6, 7. Okay. So you have assembly instructions, many assembly instructions in these pages. You probably understand, right? There are instructions. So when you first start this part, number 4, 4 was not in the memory as you click on the or type the name of the application. 4 is not in the memory. So operating system brings 4 into memory. It starts running and it tries to jump from the end of the 4 to 5 because logical address continues. All right? But it is not in the memory. So next part will be brought to memory. It could be here, it could be somewhere else because there is also paging going on. So that they don't have to be one after another because it is in the real memory. It is in if they are in the logical memory, they are one after another. The blocks pages are one after another, but in real main memory, they can be anywhere. But pages are together. The single page contains many instructions inside. But once the page is finished execution, it tries to jump to the next page. If the next page is not in the memory, that page must be brought to memory. So that is what we call demand paging. Bring a page into memory only when it is needed. So that is what demand paging is. The idea is, if the page is needed, just use it. Just try to use it. If the reference is invalid, if you are referencing to an unauthorized area, there is an abort process, interrupt. If the page is not in memory, then start an interrupt service routine, so that interrupt service routine will bring that page from hard drive to memory and restart the execution of the process by returning from the interrupt. Therefore, we call it as lazy swapper. Never put a page into main memory until it is needed. So we call it as lazy swapper. Lazy swapper. And that is what is used. Then the pager, therefore, that operation, that lazy swapper, is sometimes called as pager. Paging algorithm is executed by pager. So what is paging then? When you have a main memory, your main memory is full, and you have a hard drive. On your hard drive, you have 1, 2, 3, 4, 5 to 16. And 9 is required. So when 9 is required, one of them must be erased. So I will decide one of them to be erased, and 9 will be put into the same space. So this is called as victim. This will be a new page. So this is called as page replacement algorithm, page replacement operation. So the pager brings when the pages are needed. Pager also decides which page is the least required, so that I can delete it. I can take it out. Some pages are in the memory. For example, if the page 4 is in the memory, and if there is a reference to it, there is nothing to do. But if it is not in the memory, you have to bring it to the memory. And if there is no space, there will be one victim. And the victim memory is, if the victim memory is changed from the value, for example, that is 3, right? If this 3 is different than the content of the other 3, so we call it is dirty. If it is dirty, it must be written back to the hard drive so that the changes won't be lost. So swapping in sometimes requires swapping out, because swapping out of the victim, because victim is dirty, victim is changed from the values on the version of virtual file. Let's see. Therefore, there is a valid invalid bit. There is valid invalid bit issued into the page table if the page is in memory. We have a bit, we say it is valid. If the page is not in memory, we have an invalid bit in the page table. So that means if that page is required, you need to get it from hard drive and make it valid after the copying. So that is one of the steps of paging. If there is an invalid page during the address translation, during the address generation, if there is an invalid page, we call this issue as page fault, and then page replacement algorithm is executed. Page replacement algorithm usually gets a page from hard drive, but sometimes puts a victim back to hard drive and gets the page to memory. So sometimes it requires swapping in and out, sometimes only swapping in. At the beginning, for example, when you are starting the application, it is only swapping in if the memory is empty, one by one. So it is, although the name is replacement, sometimes there is no replacement. There is only bringing. So bringing is also counted as replacement. We have problems asking how many page faults will be. In order to have page faults, we count bringings as well, in addition to replacement that involves bringing and taking it back. That is the same thing in terms of count. So this is a nice example. The page table, when some pages are not in memory, what we have, this is our logical memory. Logical memory is from 0 to 7, so there are 8 pages in the logical memory. In our physical, in the page table, again, same size, but in physical memory, they are not there. In this configuration, I am only dealing with one application. You may see that logical memory is smaller than physical memory, but this is actually longer. So, okay, so normally it is bigger. So in the page table for this process, we have we have 0, we have 2, and we have 5. 2, 4, and 5 as the listing, as the valid things. 4 contains A, 2 contains 6, 5 contains 9, and those are valid. on the hard drive, this arrangement is the same as this arrangement. Just like the logical memory, there are addresses. So the first one and the second one and third one. If I want to go to, for example, I am running the part A and finish execution of part A, and part B is 1. 1 contains something here, but the bit is invalid. If the bit is invalid, that means page fault. So page fault, bit is invalid. I need to get B. B is after A, so it is here. So this must be that is my interrupt service routine. This might be brought into memory. So, for example, you will manage a list. Let's put B here and write 10 here, and go back to execution of code in B. So this is what happens when we have page replacement. I'm going to have that. That is page fault. If there is a reference to a page, first reference to that page will trap its software interrupt to the operating system. We call it as page fault, and operating system looks another table to decide whether there is an invalid reference, invalid or valid check, or just not in memory. If it is just not in memory, find free frame, as I did, swap page into frame with a scheduled disk operation, set the validation bit to V, and restart the instruction of the process so that it works as if nothing has happened. He or she, it is unaware of what is going on. The application is unaware of the paging operation. It's just slowing a little bit. Not little bit, seriously slowing. So this is the exact steps I was explaining. So if the instruction is referencing the point in page, the page is not there, so there is an invalid bit. Invalid bit causes software interrupt, which is trap. Software interrupt is executed. It goes back to the actual location in the disk and finds a free frame running the free frame algorithm, then updates the page table and returns the instruction. This starts the instruction. I think it is clear enough at this point. So at the beginning, there are page faults. When you start the process with no pages in memory, page 1 is also page fault. So starting is accommodated by page faults, no problem, because you are going to load it to memory. So it becomes a part of the program start. Then rest of the pages are only brought in when they are necessary. So if your program starts with a certain block of code, then here it jumps to another part in the code. Then these parts are not brought into memory, but the blocks, the pages that are containing that part is taken in. So the rest is not necessary. They don't get any page faults and any requirements. That is what we call demand paging. But sometimes you may preload certain pages if there is time. Sometimes you need to deal with victim pages. So you need to make some estimations based on how the pages are used so that they might be used again in near time. So there are algorithms, nice algorithms, depending in the results depend on what you are doing, whether you are doing machine learning, whether you are doing database or image processing or network switching. So it depends what you are doing. Sometimes one instruction, such as multiply memory 1 and memory 2 and store the result into memory 3. There are such instruction in CSE microprocessors like Intel. Multiply this memory location, the number in this location with the number in this location, and put the result in another location. And the code is in another location. Therefore, it may require 4 different pages. So that is interesting. And those pages must be continuously at the same time in the memory. Otherwise, there will be problem. When you have demand paging, hardware support speeds up the valid bit thing, just like in the memory management unit. So it is taken, the task is implemented by the memory management unit. Sometimes you are dealing with block moves, animations, for example, in block moves of data. Certain pieces of data are transferred to another part. So this may have multiple pages. This may have multiple pages in the memory. So this part will be shifted to this part. So read, write, read, write, read, write, read, write, read, write is required. Therefore, you may need, if the source and destinations are overlapping, there might be significant amount of swapping in and out. So that is interestingly complicated. These are the steps, the nightmare steps. Worst case, page is not there, save the user registers to process it. This is the interrupt service routine. Determine the interrupt was a page fault, check the page reference was legal and determine the location of the page on the disk. Issue RAID from the disk to find the free frame. Wait in queue for this device until the RAID request is serviced. Wait for the device to seek latency time. Begin the transfer to get the page. While waiting, allocate CPU to some other user because CPU must be running. Receive an interrupt from this to IO subsystem. When the IO is completed, go back. Save the registers and process state to the other user. Determine what the interrupt was from the disk. Correct the page table and other pages to show the page is not in memory. Wait for the CPU to be allocated for this process again. Restore the user registers, process state and new page table, and resume the interrupt operation. Interrupted instruction. Interrupted instruction. So go back to the process, which is a lot. But it should be done because as a result, you will work like you have more memory. And this will happen from time to time when the page is not in memory, not always. For that purpose, it is very important to find who is going to be victim page. When you are swapping the pages, who will be in, who will be out is very important. The performance calculation is usually question a lot of time. There is a page fault rate, service interruption, read the page, restart the process. So page reading is significant time. So when you have page fault rate given as a probability, you can calculate the effective access time, such as when you have p is 0, that means no page faults. All the pages I need are in memory. This is the case when logical memory is equal to physical memory, or your physical memory is good enough to contain everything you need in terms of the applications. But if the applications demand more memory at the same time, if the memory is not sufficient enough, then there is a probability that some pages are not in the memory on the disk. Therefore, p is greater than, in that case, p is greater than 1, such as like this. If p is 1, all the references are page fault. So that means you only have one frame in your virtual memory. In your physical memory, you only have one frame as a memory. So whatever you are going to execute must be put into. So with that kind of memory, with one frame, multiply M1, M2, M3 cannot be executed because this may require 4 pages. Therefore, there is a minimum amount of working memory in order to accomplish certain tasks. That will bring to Peter Denning's working set model that we will be talking in a few moments. So effective access time is 1 minus p times memory access, meaning that if the p is small, regular memory access time in nanoseconds, but with the p times the web page out, the web page in time, so which is very big number in milliseconds. So nanoseconds times 1 minus p, in a number with milliseconds time, p. So that will give you effective access time, such as memory access time with 200 nanoseconds and the page fault service time is 8 milliseconds. 1 minus p times 200 plus p times 8 milliseconds. Okay, 1 minus p times 200, p times 8 million. So 200 plus 8 million times p is effective access time. With the formula, this is the formula with 8 milliseconds. So if the p is 0001, then effective access time becomes 8.2 microseconds rather than 200 nanoseconds. It goes down to 8.2. That is nanoseconds. So this nanosecond, how much increase? Too much increase, like 50 times increase, 40 times increase. If the performance degradation is asked less than 10%, so the question will be solved as p should be smaller than 0.0000025. So that kind of probability we will be talking about in order to have this amount of 10% slowdown due to virtual memory. So virtual memory is requiring a lot of careful design on page fault rate. If the page fault rate is high, virtual memory becomes unusable solution. So that is one page fault in every 400,000 memory accesses. And keep in mind that when your page is 8 kilobytes, for example, when your page is 8 kilobytes, you probably have like 2,000 instructions, 2,000, 3,000 instructions in one page with 8 kilobyte page size. So each memory access is done by one line of instruction, and sometimes these pages contain loops. So when you have a loop in single page or multiple page, they will stay in the memory, so they will do the same memory access, and that will count to this number. So it is big, but not that frightening. So some different operating systems deal with this paging problem differently. Sometimes swap space I/O is implemented as faster I/O, even if they are on the same device. So special considerations are given to make it faster. Copy the entire process image to the swap space when your process is starting. So page in and out of swap space when things are running. That is used in earlier BSDs. In Solaris, get the program to from disk to instead of getting everything copied to virtual memory at the beginning when they are needed, get the pages from the program binary code, and if you are going to swap out, then you can write it back to virtual memory. Otherwise, that is a usual program start reading from, because there is an executable file in the hard drive. So use that executable file for the first time. That is what Solaris is and BSD is currently doing. Some mobile systems don't support swapping. They have segmentation implemented and with demand, and when there is a process asking for space, that space is given to the process that is in need. The rest is then deleted. So mobile devices believe that you may need your application again, you may switch back to your application, so they keep it in the memory because the device is always open. But if another application requires more memory, then they will discard it. So they discard it when somebody else is requiring it. Otherwise, they stay. So they don't allocate swap space usually. We have gone over copy on write. When that will be related to page sharing. When you create a child process, parent and child process initially share the same pages in memory because they have the same code base. But when the write instructions are executed in that memory, then suddenly they should be separated, because child and parent will be doing different things, so the code should be separated. So only modified pages are copied, differentiated. Unmodified pages are shared between parent and child processes, and we call it as copy and write issue. Fork and vfork are different based on their use of address space of the parent, and these are quite helpful things when you are dealing with implementations of virtualization and multiple processes are running on the same data or web services, because, for example, you are running instances of Apache at the same time to serve. So most of the code shares the same space, but some user states are shared in different locations. So some pages must be shared and stay in the main memory together. This is the visualization of this process. You have process 1 and process 2. They are using the same pages. There is a write instruction is executed. When write instruction is executed, memory manager creates the trap of software trap, so that the copy of the page is created, and then process is restarted again, so that they will continue to work as if nothing has happened. Until this, they run together. And if there is no free frame, there is a victim. There is a victim. The algorithm is called as page replacement algorithms. The performance of the page replacement depends on how you are doing it and why you are doing it. Also, same page may be brought to memory multiple times. And we ask this question in the exams, and I believe it will come in the final exam as well. So page replacement prevents too much allocation of the memory, and it modifies dirty bit to reduce overhead of page transfers. Only modified pages are transferred to disk, and page replacement completes the separation between logical memory and physical memory. Therefore, large virtual memory can be provided on a smaller physical memory using page replacement algorithms, because normally you have smaller physical page. Once you finish bringing the pages, you are finished. So what you need is send victims back and put new guys in. So that is page replacement algorithm, and makes use of the efficient memory. An instruction containing load m is the address, and m is here. That is the code. M, when you check 3 is valid. No, that is 0. That is 0, 1, 2, 3. 3 is invalid. 0 is valid because it is here. So it is in 3, which is H. So M is not in memory. M is here. So it is invalid. Then you need to find one victim, D, H, J, A, E. So let's another user. That user is trying to have B for the first page 1, and the page 1 has no associated frame, so that also needs to be brought here. But there is no free space, so some of them should be discarded and put back. For example, it could be A. A will go back, and then M will come here. That's an algorithm. So basic algorithm says find the location of desired page on disk, find the free frame. If there is a free frame, use it. If there is no free frame, use a page replacement algorithm to find the victim frame. Write the victim frame disk if it is dirty. If it is dirty, write it back. If it is not dirty, just discard it. Just think that it is empty. Think that it is empty. Then bring the desired page into newly frame, update the page table, and continue the process. Now we have potential 2 page transfers for 1 page fault, which is one swap out and then swap in. Okay. So that is the visualization. Find the victim, swap out, swap in, and reset. Update the table and go back to process. Go back to process. Well, how we do it? There is an algorithm for frame allocations. Frame allocation algorithm determines how many frames to give each process and which frames to replace. And page replacement algorithm finds what's the lowest page fault rate on both first access and re-access. We try to reduce number of page faults in an algorithm. And the behavior of the algorithms are unpredictable. Can we estimate how the program is going to behave? Deterministically, no. Statistically, yes. So we can only say this should be the best algorithm after it happens. Therefore, after it happens are called as reference string. We evaluate algorithms by running in a particular string of memory references after the program is executed and computing the number of page faults on that string. So why is that important? We check similar page reference strings and determine the behavior of the algorithm. And that kind of applications usually show similar memory access behaviors. So if that works in multiple reference strings, probably other programs will have similar reference strings so that it will be successful. We can evaluate our algorithms by known reference strings. Do you understand? So the reference string is, for example, here 70120304230 whatever. That means these are the page accesses. I need page 7, then I need page 0, then I need page 1, then I need page 2. That means in my logical memory, first I need 7. This is 7. Then I need 0. Then I need 1. Then I need 2. Then I need 0 again. So my code jumps in the memory, in the logical memory. So it shows me some kind of request. It exhibits kind of request for memory, and this is the output of that kind of request, and we call it as reference string. And these problems, these questions are solved using that reference strings. And let's solve a particular example on that. And generally, when number of frames are increasing, we expect number of page faults to decrease generally, but sometimes not. Bazen toparlayabilir. If you have only one frame, maximum number of pages has occurred. As you increase number of pages, number of page faults are reduced. The algorithms are various. The easiest one is the first in, first out algorithm. First in, first out algorithm says the first page that is brought into memory should be the one which is less needed because it is old. That is the original idea. Yani senin işin bitti kardeşim. Sen geleli çok olmuş. Hani şöyle düşünmüyor. Sen gelmişsin ama sen buranın eski adamısın. Muhtemelen her zaman sana ihtiyaç var diye düşünebilir ama öyle düşünmüyor. Sen eski gelmişsin. Hemen git diyor yani. Yeteri kadar burada durmuşsun diyor. So that is what we call first in first out algorithm, and the problems are like this. When you have 3 frames in memory, 3 physical frames in memory, that is with the first page fault behavior. So the first page will be put into memory. Second, from the reference string, will be put into 0 into memory. Then 1 will be put into memory. Then 2. When I ask for 2, there is no free frame, so there will be one victim. Who is the victim? 7, because that is the first one. So first in, first out. So 2 comes there. Then I need 0. 0 is there, so no page fault. Then 3. 3 comes here because now at that point 0 is the oldest. And then 0 is needed, no problem. 4 is needed. Who is the oldest guy? 2, because no, 0 is not there, so 0 is written here. When 4 comes, 2 is the oldest. 2 comes and 3 comes, no problem. 2 comes, there is a problem because 2 is gone. 3 is then replaced with the 0 because 0 is the oldest one, and so on. So we count these page faults, including the initial loss. So this is the important part. They are also page faults. So you don't have to have replacement. So how many when I ask how many page faults we have 15. We don't have 12. Please make note of this because you are doing this in exam incorrectly. Some of you are doing this in exam incorrectly. You say 12 and it is not the correct answer. Sometimes adding more frames can cause more page faults because numbers don't match, numbers don't align. We call it as Belady's anomaly, and I will have an image like this. So with the number of page faults when the frame size is 1, 12 page faults, 2, again 3, 9 page faults, 4, 10 page faults. So it can happen because the number you need, the page you need is just taken away by the previous request, or due to order changes, due to the certain changes. This is not always the case, but this may happen in first in, first out. Optimal algorithm. What is the optimal algorithm? Optimal algorithm can only be determined after the request has come. So optimal algorithm cannot be used by an algorithm. It can be used by you to analyze. Because we cannot read the future. We can only read the future on the past data for analysis. The idea is to replace the page that will not be used for the longest period of time. So that is used to test the efficiency of algorithms against the perfect case. So optimal algorithm is the benchmark for the best case. The other algorithms are trying to reach to the performance of the optimal algorithm. But since we cannot predict how the program is going to behave, since the string is happening on the fly, so this is a problem, we know it, but in execution we cannot predict future. So algorithm will only look at the time spots that it is working on. Therefore, when this comes, for example, you can only see what you have, and that you don't know the future. So at this point, decisions are made based on the previous part. But in optimal algorithm, you know what is going to come as a hand analysis tool. So you can do much better with the same string. As you see, number of page faults are significantly smaller. To approximate optimal algorithm, one strategy is least recently used. The idea is to replace a page that has not been used in the most amount of time. So it means if I haven't used it recently, I think it is old. But if it is old, but if I am still using it, I don't consider it as an old. So the definition of age is introduced, which will be different than first in. First in is not the age. Age is last touch. It is related to last activity. So if it was early comer but active lately, then we consider it as a new. So we will discard old ones. That means they may come later, but we haven't been using it for quite some time than others. It is an assumption. May not be true. It can be the way that if I haven't been using certain page, maybe I will use it in coming time because I want it that way. My program works that way. So this is also an assumption. This will be giving for this kind of string. At each time spot, we again look back, but the determination of the new is based on last recently used information. Here we have, instead of 15, now we have 12 faults, page faults. It is better than first in, first out, but worse than optimal algorithm. In the optimal algorithm, how many we have? 1, 2, 3. 3 is obviously always there. 4, 5, 6, 7, 8, 9. So 9 page faults is optimal algorithm, and with least recently used algorithm, I have 12 page faults, which is smaller than 15 but larger than 12. The aging must be implemented. So aging is implemented with the counter. Therefore, in the page table, we have invalid, valid bit, we have reference ID, etc. And then we also have a counter to indicate the age, that is indicating whether the page is new or old. It could be binary counter, it could be counting counter. If it is binary counter, the information is only between new and old. If it is new, when you reach, you update it. Like a bird going to a tree. When you go to a tree, it becomes new. So it is new. If you don't touch, it is old. So that kind of referencing and making new and old is implemented in the memory management unit table. When the page needs to be changed, look at the counters to find the smallest value. That can be implemented in the stack format. When the page is referenced, move it to top. If the page is not referenced, it will stay at the bottom. So when you are going to select the victim page, consume the victim pages from the bottom of the stack. That is one idea. And optimal algorithms and least recently used algorithms are cases of stack algorithms that don't have Belady's anomaly. So first in, first out has Belady's anomaly, but the least recently used and optimal algorithm don't have Belady's anomaly issues. This is the stack algorithm for referencing, finding referencing. So for example, 4 is referenced, then the 7 is referenced, and the 0 is referenced, and the 7 is referenced. 7. So 7 goes up. At the top. 1 is referenced. 0 is referenced. 7 is here at that time. 1 is referenced. 1 is there. 7 goes down. 0 is referenced here. 1 is referenced here. 2 is referenced. 7 is referenced. So here 7 is referenced. 7 is at the top. When you are going to consume, you take numbers from the bottom. Telefona bakayım. So most recently referenced pages are put on top. For example, when I reference 0 here, again, I put 0 at the top and move these down. So at this point, that is before A. At this point, that is before B. After B. Because 7 is 7 is referenced there, so 7 goes to the top, taken from the bottom, goes from here to here, with the reference done it just before the B. Again, counting is difficult, so instead you may need to have age 0 and age 1. So depending on your implementation, 1 may mean new or 0 may mean new, no problem. So we call it as clock replacement algorithms. If you have 0 as the clock, replace it, it's a victim. If you have 1, so it must be new. Make it to 0 by giving a second chance, and replace that page next time. But if it is refreshed, if it is accessed again, its reference bit is again set to 0, so it becomes new again. So one side puts the clocks down, and as you reference, it increases. So if the page is not referenced and the clock is aging, then that becomes the victim, using 0 and 1 bits. And dealing with bits in memory management unit is much easier than dealing with counters, because you can operate in gates and binaries, etc. So it operates faster. This is the second chance algorithm with pages. So next victim, that becomes 0 after one page replacement. That can be also enhanced with multiple reference bit and modify bit. This is what I have been saying. If there is a reference bit, it is being used, and also there is a clock together, recently used, clean, probably will be used again soon, probably will be used again, but modified, so it is dirty. Neither used nor modified, best place to replace, not recently used but modified, dirty but not used. So I might be ordering among these, and your algorithm may work a little bit faster. Counting algorithms are binary or regular counting algorithms. Those algorithms have two different approaches. One of them is least frequently used algorithm. The other one is most frequently used algorithm. Least frequently used algorithm replace the pages with smallest count. So how many times a page is used is counted. If the page is used a lot, so its counter number is big, the algorithm finds the victim with the smallest number. Most frequently used algorithm says you have been using it too much, and the other one has no count. It is new. So new has no reference to it because it is new. Since it is new, I will use it. So that is the starting point of the most frequently used algorithm, and it is only good for certain type of tasks. When new things are important, and we'll have more reference in those pages. Usually, the memory manager keeps the list of these free frames and pages and also keep the dirty information together, and that will help to find the correct victim much better. So these are additional considerations. One of them is the page buffering algorithm. Disks are used for this operation, and the operating system is actually making assumptions and estimations about future memory accesses. Some applications have better knowledge, such as databases. Memory-intensive applications can cause double buffering. OS keeps copy of the memory I/O. So when there is memory I/O, the issues are more complex because I/O takes time, and during the I/O, you shouldn't take the page out because there is an I/O. So it is solved by I/O interlock, and sometimes applications want that page, so there must be a declaration. There must be a declaration mechanism to lock the page free from the page replacement algorithm, and so on. So locking and bypasses, etc. I have said this in IBM machine, for example, ssmove instruction may take 6 pages. So one instruction may have 6 pages. So in order to execute that instruction, minimum 6 pages are required. So one is not enough. Therefore, there is a minimum set of working size, and that is discussed in working set model. Some operating systems allocate equal amounts to all processes, such as among 100 frames, 20 frames per each process, and each process are equal, so 20, 20, 20, 20, 20. So if this process is very heavy on memory, it will do a lot of page replacement. This will be lazy, slow-moving, and peaceful. It may not have that many page faults. So the operating system may decide to shift some of the pages from this process P2 to P1, so that P2 will exhibit lower page fault rate, because the overall page fault rate, total page fault, will be affecting the complete operating system performance. So operating system can balance the allocation of free frames based on the number of page faults occurring for each process. One idea is make allocation to the size of the process, but it is not as also good, because big code doesn't mean that it is going to work altogether. Code might be big, but it could be nice. So it is also an interesting topic. What kind of memory will be reserved for each process, depending on its behavior, dynamic behavior on the memory. Generally, if you are the student versus professor process will have more memory. So that's my idea. But generally, there can be priority. That priority can be dynamically changed. So here you go. We have an algorithm. If PI generates a page fault, select for replacement one of its frames, and select for the replacement a frame from the process with lower priority number. So victim will be an element of the low priority one. The multiple processes working P1, P2, P3, P4, P5. So Each one has its own free frame list. That is what local replacement is. But if the paging algorithm is running on the global sense, in the if the set of all free frames are used as a list, that is what we call global replacement. If the page replacement is done locally, that is done with local replacement algorithm. Throughput is increased in this. Less throughput, there is an underutilization of memory. Some processes are very lazy. Some processes are very heavy on memory and create more software and create more page faults. But in this one, per process performance is more controlled. On top of this, there is also virtualization, operating system virtualization going on in recent trend. In some cases, with the new structures, memory access speed is not the same. So this is new to this chapter. Speed of the memory can be different. Some of the system boards containing CPU and memory over the system bus may have slower parts of the memory and may have fast parts of the memory on the same address line. So optimal performance comes from the using the memory close to the CPU where the thread is scheduled. So when you have multiple CPUs and single memory and copies of these memories on near CPU, so being closer, this is the definition, being closer changes the performance. So then this page replacement algorithm should also consider to replace and find the victim based on the distance of the memory to the process. Yeah. If there is not enough pages to do the task, if the thing is always creating page faults rather than working, if the page fault rate is increasing too much, if the process cannot hold certain pages to work, such as you are copying one piece of block to another piece of block in the memory, when you are doing block copy, that must fit into certain number of pages. Otherwise, you have to load and unload, load, unload at each line of the code. One line of the code will require one line of the one interrupt service routine to swap. So that will be inoperable. We call that issue as thrashing. In the thrashing, we have a page fault, replacing frame, but we need that frame back. We need the victim back. So it leads to low CPU utilization. If the CPU utilization is low, the scheduler thinks that it should increase the utilization by adding more process, and the performance goes down further. And that means if the process is busy swapping in and out in the virtual memory structure, no job is performed, only swapping is performed. So as you increase number of processes working together in a certain size of memory, it increases, utilization increases, then after then, suddenly input output, page in and out dominates, and in a fast fashion, CPU utilization goes down, and machine is now busy, hard drive is busy as crazy, swapping in and out, but not executing instructions. So that happens, that usually happened a lot in operating systems in earlier years. Hard drive is running like crazy, computer is freezing, something is happening, but I am not working. So that brings us the locality issue. If the locality is bigger than the space that we have, thrashing occurs. What is that? This is interesting. This is the memory map of an application in time. At the beginning, these parts are required. Then these parts are required. Then these parts are required. At the end of the execution, these parts are required, but not this part is required. So how many pages if these are one page, actually they are not, but if those are one page, how many pages I need generally for this program to work without much page faults? Probably 1, 2, 3, 4, 5, 6, 7, 8, and maybe 9. So 9 pages are usually for this application, because here, for example, this part is not used. This part is not used, only used here and here a bit. So 7, 8, 9 pages are enough. So if I start with 2 or 3 pages, there will be a lot of swapping, maybe thrashing, because the power utilization will be reduced significantly. So that is what we call working set model. Working set means in order to perform a task in a sufficient speed, I need to have them in my possession. I have to have certain pages in memory in order to operate. Otherwise, I will be busy with in and out. It is like cooking a food in the kitchen with the items taken from your neighbor. You can take things from your neighbor, but as you are cooking, do you go and ask things from the neighbor one by one? So if you need several things, at least you have to collect them, and you should not give it back before completing the food, before preparing the food, because you will need it again. So that defines the working set for any kind of task in computer science or in mechanical engineering and other kinds of industrial process engineering issues. The working set model is always is an issue. So, for example, when you have 10,000 instructions, 10,000 instructions are a working set, so they will require certain pages. Once the pages are loaded, there shouldn't be any further page faults. Otherwise, the performance will slow down. So, for each process, there is a working set determined by delta. So big delta is the sum of small deltas of P1, P2, P3, Pn. So sum of these working sets gives me D. If D is bigger than what I have, then there will be thrashing. So when D is approaching M, we need to be careful and we need to stop certain processes, swap out certain processes so that memory will be free for the processes that are already trying to work. Otherwise, no food is finished because of the items going back and forth between neighbors. Okay, this is one example of the reference table, and this is the size of the working set. This is another working set. These are two different working sets. And if the D is greater than M, the memory, then suspend certain processes. It is like a deadlock avoidance algorithm. It is distantly related to deadlock avoidance algorithm, Banker's algorithm. Example of this, delta is 10,000. Every 5,000 time units, timer interrupts. So 2 bits for each page. When timer interrupts, copy and sets the values of all reference bits to 0. So it is not accurate because there is only 10,000 working set size. It may not be true, but it is okay. When you are trying to make it better, make the calculation in more frequent time. So before thrashing occurs, you may predict it in much faster rate. So 10 bits of reference counter, page reference counter for 10,000 instructions. When number of frames increase, page fault rate decreases. So acceptable page fault frequency is very low, 0.000000001 or something like that is acceptable. So our algorithm tries to set this page fault algorithm between upper and lower bounds. Then we say it is an acceptable number by playing with the victim selection and page giving pages to processes. Usually, working set changes over time. Sometimes there are peaks, sometimes there are low demands, but this kind of behavior is seen in a given working set, generally, or different set, but page fault rate is increased and decreased, a little increase, decrease, and then stabilize. So one of them is usually the working set. I think we are done today. I will continue with this and disk files because this is related with the disk. Next week and the week after next week, your presentations will start. If you have any questions, let me know at this moment.
Hocam sunumlar nasıl olacak? Yani biraz bilgi verir misiniz acaba?